I want to go quickly through a bunch of examples of how we use trig functions to simplify expressions. Sometimes it's not necessarily simplifying, it's just making it look different. But there's so many so many relationships between the trig functions that they just are extraordinarily useful in making expressions look different. Anyway, if you feel like I'm going too fast, feel free to pause, rewind, and listen again. I just want to get a bunch of examples out here. So, we'll start simple and work our way up here. How about something like the secant divided by the cosecant? So, that looks ugly. How about the secant of theta divided by the cosecant of theta? Okay, can I simplify that anyway? Can I rewrite it to maybe look a little nicer? Well, I'm going to use a bunch of those basic identities to see what I can do. First of all, when I was learning this, one of the basic things I figured out really fast was that the reciprocal identities and the quotient identities are your friends. I would, for instance, on this one, see secant and cosecant and say, oh my goodness, I'd much rather use sine and cosine. That is, I would much rather see this written as the secant is 1 over the cosine of theta, right? That's a reciprocal identity. And the cosecant is 1 over the sine of theta. Then it's like, well, yeah, that's a big fraction, but I know how to divide fractions. That is, I know that this is equal to 1 over the cosine theta times sine theta over cosine theta. No, wait a minute, what am I doing? This is yeah, there we go. I'm just flipping the bottom fraction upside down and multiplying. I'm getting ahead of myself here. Now when I multiply fractions, you multiply the numerators. Sine theta on the top, cosine theta on the bottom. And, well, is that simpler? I mean, I had one trig function divided by another, now I have sine divided by cosine. You say, oh, wait, I mean, that looks of similar complexity, but sine divided by cosine I recognize because of a quotient rule. Sine divided by cosine is tangent theta. So indeed, I think I have simplified it by going from here to there. Okay. Other things. How about something like this one? E.g. is, for example, in Latin. How about 1 over 1 plus the cotangent squared theta? This is one where I would probably do it differently now than I would have when I was your age. That is, when I was taking a trig class, pre-calc class. I really liked sine and cosine, and I didn't really like the other one. So I would have a tendency to look at that cotangent squared and want to convert it immediately to sine squareds and cosine squareds. But later on, as I learned more, I learned that, oh yeah, there's more identities that I can use. I can use, for instance, that 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. And that if I can get myself to, think in terms of cosecants and cotangents rather than just sines and cosines, I might be able to simplify my life some. So this could be, that denominator is already set up to just be 1 over the cosecant squared of theta. Well, the reciprocal of the cosecant is the sine, so this must just be the sine squared of theta, right? Remember, 1 over cosecant squared means 1 over cosecant times cosecant. There's 2 cosecant thetas being multiplied in the denominator. So that's the same as having 2 sines multiplied in the numerator. Okay. Now, what I would have done up until only a couple of years ago, probably, I would have instead looked at it this way. There's not just one way to do these things. There may be a quickest way, but you don't always see the quickest way. So I would have looked at the cotangent and said, hey, that's the cosine theta over the sine theta. But it wasn't just cotangent, it was cotangent squared, so that whole thing is squared. So the numerator squared and the denominator squared. Right? And then I'd say, oh, this is a big fraction. This has got 3 layers, and how do I simplify a 3-layer fraction? Well, a couple ways you can think of it. Some people say, well, get a common denominator, and then you're dividing by this fraction. I have a tendency to say, I'm going to multiply by 1, and the 1 that I choose is, when I see denominators, I'm going to multiply by them. So I'm going to multiply top and bottom by sine squared theta. The 1 times sine squared theta is sine squared theta. Down on the bottom, this distributes into both of those, so it looks like the sine squared theta times 1 is sine squared theta. The sine squared theta times this fraction, well, the sine squareds cancel out, and that's just a cosine squared theta. I then recognize the Pythagorean relationship. Right? Up here, it took me recognizing this Pythagorean relationship. Now I'm saying, well, instead, I can maybe recognize that one. Sine squared theta plus cosine squared theta is 1. So I've got a sine squared theta on the top, I've got a 1 on the bottom, which of course is just sine squared theta. I ended up in the same place, right? This one maybe took me a little bit longer. However, back in the days when I wasn't as comfortable with cosecants and cotangents, I would much rather have done this. I could do it, I could get it right. There's absolutely nothing wrong with this approach here. Okay? Maybe this is a little quicker if you recognize that identity. The more of the identities that you have at your disposal, ready to use, that you understand and can work with, the quicker this is going to go for you. When you got to keep going back and looking at those identities, saying which one can I use? What? It's just going to take a while. Let me do another one here. How about something like, I got several of them checked off. This one looks kind of fun. I'm getting these out of the homework section in the pre-calc book. The end of section 9.1's got a bunch of these problems. I didn't assign them as homework or anything, but certainly if you want to look in that book, you're more than welcome to. There's a bunch of them. So anyway, here's an expression. And one of the first things that jumps out at me on this one is like, oh, that numerator is equal to 1, right? The answer is no. No, it's not, because there's not a plus sign in between, right? Here, with a plus sign, that was 1, but no. So, let's see. Can I simplify this? Well, it's already in terms of sines and cosines, so I can't do that. One of the things I can do is I can very carefully here, I can see some people wanting to do some incorrect algebra and say, oh, cancel out the cosines and cancel out the sines, which is not correct, because although this cosine is a factor of the denominator and is ready to be canceled out, this cosine up here is not a factor of the numerator. The numerator is a sum of two things. It's not factored. It's not a product of things. So you can't cancel anything yet. However, I can use a distributive property and say that this denominator is divided into both of those pieces of the numerator. So this is cosine squared theta divided by sine theta cos theta, and then minus sine squared theta over sine theta cos theta. Right? So I've taken this one fraction and turned it into two separate fractions that I'm subtracting. Now each of these fractions individually is ready to be canceled. This is just a product of two cosines on the top. This is a product of a sine and a cosine on the bottom. So one of those cosines cancels out. One of the cosines on the top cancels out with the one on the bottom, leaving just a cosine on the top and the sine on the bottom. Likewise over here, this is a product of two sines. This is the sine of theta and the cosine of theta multiplied together. This is all multiplication and division, so I can cancel this sine out with one of those. All right. In this stage, I cannot, because there's a subtraction here. This one individually, this fraction and that fraction, I can cancel stuff out. Okay. So what I'm left with is a cosine theta here and a sine theta there, and here I've got a sine theta on the top and a cosine theta on the bottom. And now I'm thinking, oh, that looks like some quotient identities. Certainly sine theta over cosine theta I recognize as tangent theta. And so this one must be up and down. It must be the cotangent of theta. So yeah, this big old expression right here is equal to that one. Okay. Let's do one more. I've got, here's an example. Again, it's going to start all in terms of sines and cosines. So I'm not going to switch to sines and cosines. So that could have started as a cotangent, I guess. And let's put this as the sine of theta over 1 plus the cosine of theta. Okay. And see how we might simplify this. Again, I saw that was cotangent theta, but I don't see how that helps me in adding it to this thing over here. No, so I guess I'm at the point where it's like, well, I'm adding two fractions together. Let's do that. How do you add two fractions? Well, you got to get a common denominator. So I've got to multiply this fraction top and bottom by that denominator. So I've got cosine theta over sine theta. I'm multiplying by 1, right? By saying multiply top and bottom by the same thing. You're saying I'm multiplying by 1, but I'm choosing how I want that 1 to look. Likewise over here, I've got to take this fraction and multiply top and bottom by this denominator over here. So I'm going to multiply top and bottom by sine theta. Now I'm going to be a little careful here and note that there's distributive properties that have to happen, so I'm going to put some things in parentheses. It's the sine theta times all of that. It's the sine theta times all of this. Okay. Now, so that thing right there was equal to this. What's going to happen? I'm going to leave the denominator multiplied. I'm hoping that something's going to cancel out. And the denominator is just sine theta times 1 plus cosine theta. Right? I've managed to get a common denominator, so that's what it is. The numerator is going to multiply out and see if I can get some things to combine, maybe. I've got cosine theta times 1. And I've got a cosine theta plus times cosine theta, so that's a cosine squared theta. Here I've just got sine squared theta. Oh, that's nice. As soon as I write it down, it's like, oh, look at that. I got a sine squared theta and a cosine squared theta added together. Woohoo! Those are going to add up to 1, right? That's a Pythagorean identity right there. So I've got a cosine theta here plus 1. All of that stuff right here. This whole stuff, come on now, turned into a 1. And so the cosine was already there. And the denominator, I've got a sine theta and a 1 plus cosine theta. Oops. 1 plus cosine theta. And I have the whole numerator here is the same as one of the factors on the bottom. This is kind of serendipitous. I thought I was going to have to stop at this stage. But since this numerator is all equal to that one factor, think of it as this thing times 1. So I've got this thing factored as a product of two things. I've got the denominator factored as a product of two things, and it's the same factor on the top and the bottom. This is the same as that. So I end up with 1 over sine theta, which I can rewrite if I want as the cosecant of theta. So this whole big thing, this fraction plus that fraction, turned out to be equal to the cosecant of theta. It's amazing that what trig functions can do, how they simplify down and combine together, and it makes them very powerful tools, as we'll see, particularly when we get into calculus, and how we can use these properties to help us solve lots of problems here. So anyway, there's a bunch of examples of simplifying using some basic identities.